So Bernard, welcome to
Thank
the
you.
Duke's Retreats here in Khandala. It's a great pleasure to have the chance to chat to you about your lifetime of working in the field of gravitational wave astrophysics. Perhaps you could begin by just telling us a bit about what brings you here to this meeting and who you are.
Okay, so I'm here, like you are, for a meeting to celebrate the beginning of the LIGO-India project. And LIGO-India is a new gravitational wave detector that's going to be built in India and will be an identical copy to the two American detectors that have made scientific history by detecting gravitational waves for the first time. So we're delighted to see this expansion of the network, and we are here to talk about the science that it's going to bring us. And who am I? My name is Bernard Schutz, and I've been working in this field for 30 or 40 years. I'm a professor at Cardiff University in Wales, and I'm also an emeritus director of the Albert Einstein Institute and Max Planck Institute in Potsdam, just outside Berlin, in Germany. In both of those occupations, I've devoted a great deal of time to gravitational astrophysics.
Mm-hmm. Great. So many of our followers, like me, may have first learned about general relativity from your textbooks. So perhaps you're the ideal person to begin with some very general questions about just the nature of gravity and what are gravitational waves. So we've already mentioned gravitational waves several times, so maybe let's just rewind a little and think about what exactly gravitational waves are.
Gravitational waves are relatively easy, I think, to conceptualize. So one of the fundamental principles of Einstein's relativity is that nothing can go faster than light. No influence can go faster than light. And so if you disturb gravity in some location, and that's happening all the time when binary stars are going around one another, then if you're standing nearby, the gravitational field produced by those stars will be changing in your neighborhood. If you're very far away, you can't get wind of those changes until a certain delay, which is the delay it takes that information to go. And so if these changes are moving through space, these changes in gravity are moving through space, we call them waves, and those are what gravitational waves are. Has to be an aspect of every theory of gravity. It was predicted first by Einstein's theory. And in Einstein's theory, it's relatively simple, if you like, because they go exactly at the speed of light.
Mm-hmm. So those predictions in Einstein's theory take us all the way back to the early 20th century, and yet their detection only took place in the early 21st century. So how come it took so long?
Yeah, Einstein was ahead of his time in this respect. It was something he thought would never happen. Mm-hmm. And indeed, even today, it might not be possible if the universe was as Einstein conceived it, because he thought of ordinary stars and planets which do disturb gravity and do give off gravitational waves, but they're so weak that even today they would be undetectable. What Einstein didn't know about was that the universe is filled with systems which are much more relativistic, that there are actually consequences. Our understanding of them comes from our understanding of gravity from his theory. Mm-hmm. But he didn't have any idea that there might be binary systems of black holes, with black holes going around each other. And not just going around each other, but so close that the gravitational waves that they're emitting are carrying away energy, and the stars are getting closer and closer and closer together, the black holes, and they will merge together. Mm-hmm. We have actually detected the gravitational waves from events like that with our detectors. Einstein had no concept that these things might be happening.
So we'll think about exactly how those detectors work in a moment, but I guess maybe the next milestone to consider is, as you just said, that Einstein was ahead of his time. He didn't imagine that such extreme objects like black holes would exist. So before we think exactly what a black hole is, what's so special about having two black holes orbiting each other? Why is that especially good conditions to create gravitational waves?
In Einstein's theory, to get really strong gravitational waves, you have to have objects that are going close to the speed of light. Mm-hmm. And you have to have strong gravitational fields. And so if you have ordinary stars in a binary system, they're not going anywhere near the speed of light because they're just ordinary matter. And in ordinary matter, sound speeds and every other kind of speed is much, much less than the speed of light. But with black holes, you have a huge amount of mass concentrated in a very, very small region. And so you can get them so close to one another before they merge together, you can get them so close to one another that their orbital speeds are a good fraction of the speed of light. And that's what makes the gravitational waves really strong, and that's why they're a good target for our detectors.
So to get a black hole, you want to have a huge amount of mass in a relatively small volume, as you just said. So how do you do that? How do you make a black hole so that later, if it teams up with another one, it might produce the kind of gravitational waves that we observe?
Yeah. Maybe a different question is, how do you avoid making a black hole?
Sure.
Because a star like our sun eventually runs out of energy. It's creating the light that keeps us alive through nuclear reactions in the center. But there's a finite amount of mass in the sun. Eventually those nuclear reactions are going to be burnt out. And the only thing, gravity is still there. If the sun is not able to push out from the inside with all this radiation against its outer layers, then gravity is going to make the sun contract. And so the question is, why would perhaps the sun not form a black hole? Why wouldn't that happen? And it's remarkable that the sun would stop at some radius about the size of the Earth and form a white dwarf for reasons that have to do with quantum mechanics and the Heisenberg uncertainty principle and the fact that it's tough to squash electrons into small volumes because they don't like being squashed together, and so there's an escape clause for stars like the sun, which comes from Heisenberg. But in Einstein's theory, without quantum mechanics, the sun should just collapse down eventually to form a black hole. With bigger stars that are 10 times or 20 times the mass of the sun, which there are quite a number, although the sun is much more of a typical star, but there's still stars that are much more massive than the sun. The contraction overwhelms those forces of Heisenberg and so on that come from quantum mechanics. A white dwarf is not in the future for those stars. They just keep contracting down. They reach a stage where they might still try to form a neutron star, which is an even more compact version of a white dwarf, and again supported by some quantum mechanical uncertainty forces to do with neutrons instead of electrons. But even so, if there's a lot of mass, that doesn't work either, and the inevitable inward pull of gravity succeeds. So the question is, what happens when something just keeps collapsing? In Newton's old theory of gravity, before Einstein, the answer would be it just forms, goes down to a point or something like that. It's a weird but accessible object. But with Einstein, you have, again, it comes back to the limit on the speed of light. If it gets, if you take something of any mass and you contract it down and make it smaller and smaller and smaller, the escape speed increases. It gets harder and harder to get away. To get a satellite off the surface of the Earth, you have to shoot it up with a rocket with a certain escape speed. If we made the Earth smaller, that escape speed would be higher. Inevitably, if you make things smaller, the escape speed reaches the speed of light. After that, nothing will get away, and it's what we call a black hole. Now, interestingly, even in the 18th century, scientists speculated about, even within Newton's theory, black stars, dark stars, because they knew that light traveled at a finite speed, and so they knew that it'd be possible in principle to have an object that light couldn't get away from. But now we know more about gravity than they did, and we can describe the object, and it's a black hole.
So we've got black holes that exist because, as you said, in their case, there's nothing to stop the gravitational collapse that provides the escape clause for stars like the sun or somewhat more massive stars that become neutron stars. And those black holes, when they're orbiting around each other, they can radiate away gravitational waves, a lot of energy in the form of gravitational waves. So if nothing can escape from a black hole, but two black holes orbiting around each other can radiate gravitational waves, where do the gravitational waves come from?
Yeah, they're coming from the stirring up of gravity outside of the black holes. So it's the disturbance that they're making in the external gravitational environment, which mainly ripples out. It's like if you drop a rock in a pond, most of the waves will ripple out. Some of the waves might come back in and reflect in or something on the rock, but and some that happens with the black holes too. But most of the waves will just go out. There's nothing actually coming out from the inside the black holes.
Yeah. So let's think about how much energy is produced in one of those events, and as members of the LIGO collaboration, we were both incredibly excited when that first detection took place in 2015. And I remember one of the numbers that really did blow me away, and just, I still occasionally wake up at night and think, wow, how did that happen? You had two stars, roughly about 30 times the mass of the sun, two black holes combining to form a new black hole. And in that process, just a fraction of a second, about 3 times the mass of the sun was released in the form of gravitational wave energy. So that feels like a colossal amount of energy, and yet they're so hard to detect. So can we make sense of that kind of paradox almost, that you've got this amazing reservoir of energy and yet we can't seem to tap into it?
First of all, let's join in our amazement at the 3 solar masses of energy. I mean, converting 3 times the mass of the sun and letting that energy go is an extraordinary event. We think in terms of hydrogen bombs and things like that being extraordinary events, and they convert a small fraction of their own mass into energy. That's nothing like what's going on in the sun, and yet it did happen in less than a second. So there's no way around the astonishment. It is really a mega event, and if you ask what is the luminosity in energy terms, luminosity is defined as the rate at which energy is coming out, the energy per unit time. For that brief fraction of a second, the luminosity was bigger than the total luminosity of the entire rest of the universe. If you add up all the energy coming out of all the stars in the entire universe, that doesn't add up to as much as was coming out of that merger system in that fraction of a second. Didn't last long, but it was the only game in town for about 200 milliseconds.
So for hundreds of years, we've been able to observe that luminosity coming out from all those stars in the universe.
That's right.
And indeed, for thousands of years, because we can do it with our eyes, but we can do it better with telescopes. So how does that connect to the method that we use to detect gravitational waves? Is it different? Is it similar?
It's very different, and it is related to the paradox that they're difficult for us to detect, and the energy coming through our detectors was still stupendous, even though that event was 1 billion light years away. It was still comparable in brightness in energy terms to the full moon, but we couldn't see it with our eyes. Whereas we had no trouble seeing the full moon, because this is a gravitational disturbance. And it's a very weak gravity. I mean, gravity is itself very weak, and I'll come back to the question of exactly how gravity is acting, but gravity is very weak, and the effect on our detectors is extraordinarily weak. And the way I can understand that is to use an analogy or a reference in physics that I learned from my colleague Carsten Danzmann in Germany, which is if you look at solid materials, the speed at which waves travel, let's say, is related to how stiff they are. And so water, you can watch the waves leisurely traveling across the surface of water. If those waves lap up against, let's say, a steel bar, some of that energy goes into the bar as sound waves, and that goes shooting down the bar, because the bar is really a much stiffer medium, and the wave speed is higher. But the thing is, you can't see that in the bar. The waves are really tiny. Those, even though you could see the waves in the water, you won't see the waves in the bar, because with a really stiff medium, it doesn't show very much. The deformation is much tinier. Well, if you extrapolate that to a medium in which the waves travel at the speed of light, which is space itself carrying gravitational waves, the waves are traveling at the speed of light. That has to be the stiffest medium that you can conceive of, because it's the fastest speed that you can conceive of.
And yet electromagnetic waves travel at the speed of light, but is the key difference there do with their kind of relationship to the medium itself?
It is, because what we're talking about here is waves carried by space itself. And the distortion in space is so tiny because the waves are going so fast and the medium is so stiff that it's really hard to detect. Whereas with electromagnetic waves, they are carrying a completely different kind of force, the electric force, and we are set up, our eyes are set up to couple to that.
So those fundamental differences between the gravitational force and the other forces, the electromagnetic forces, is tied up with the whole issue of gravity being weak. But I guess it also provides us with some exciting possibilities for the future, the kinds of questions that we might use gravitational waves to try to answer. So maybe we'll talk a bit about those as we go along, but just before we get on to the future, let's look at where we are in the present. So that first detection in 2015, super exciting, a mind-blowing amount of energy released in that fraction of a second. What else have we learned since then, sort of 3.5 years down the line?
In the 3.5 years, we've detected about 10 such systems. We haven't been observing continuously. We had periods where we were upgrading the instruments, but over that period of time, when we were observing, we had 10 black hole merger events that have told us that the first system that we saw wasn't as strikingly unusual or unexpected as we thought in the beginning. I'm a theorist, and I spent a lot of time predicting what kinds of things we might be able to see. I didn't ever predict that we would have detected two black holes of the large masses that we did observe. Both those black holes had masses bigger than 30 times the mass of the sun. So if you can imagine their progenitor stars were even much more massive than that, to have collapsed and formed 30 solar masses, and these were in binary systems, so you had two stars like that going around each other, and the two black holes orbited for billions of years before they merged. Well, I hadn't believed that we would see anything as massive as that, and yet we continue to see systems like that.
Do you think it's too soon to say what that might tell us about the sort of prehistory of that system? Or what kind of ideas are there already around?
There are ideas. In fact, other people were predicting. I was not so clever, but other people were predicting that if these stars had formed originally in clouds of gas, and stars are forming in the galaxy all the time, and in other galaxies all the time. But to get stars like this, you had to form them in clouds of gas that were relatively free of the kind of pollution that happens as galaxies age, namely free of heavy elements, what we call heavy elements. Just pure hydrogen and helium, the best kind of medium for forming really massive stars. Now, in the present age of the universe, our galaxy has been through generations and generations of stars, which have produced lots of other elements, of which we're made, so we're products of this wonderful pollution. But gas clouds that contain elements like that form smaller stars. So what it's telling us is that either these things were really old and they formed very early on, or there are pockets somewhere in galaxies
relatively unpolluted,
relatively unpolluted, and you can form them. That's one possibility. Another possibility is that they form in other ways in cluster of stars, which is also possible. But we'll get more statistics. We'll probably settle that.
Well, we'll come back to those black holes, because I guess that's starting to sound like what astronomers do conventionally, which is they study populations. They make inferences about sets of objects
That's
rather
right.
than individual objects.
That's right.
But before we get on to more of that and what the future might hold, of course, there's another event that we saw in August 2017.
That's right. That's right. So we saw these 10 black hole events, but then we had the really spectacular one on the 17th of August in 2017. And that was 2 neutron stars. Now, black hole events, spectacular as they are to think about, and spectacular in terms of the energy, are quiet in all other ways because they're black. You can't really see anything happening.
Yeah.
2 neutron stars, they haven't yet collapsed to black holes, and so they're real matter, and when they collide, well, they also form binaries, and they also merge together through emitting gravitational waves, losing energy. The binary gets closer and closer and closer, and they finally merge. But when they merge, and they're going at very close to the speed of light when they slam together, there's a huge explosion. And that's an explosion that's called a kilonova. And there's also a remnant left behind that might remain as a neutron star, might have collapsed to a black hole. That's not such a clear outcome right now.
Yeah.
But what we did see, because we were able to alert our astronomy colleagues, we got the gravitational waves, we recognized something was happening, and so we were able to send out an alert to astronomers. So within half a day, we had telescopes identifying where this explosion had happened on the sky and zooming in on it and measuring things. And this was an absolutely fantastic event.
Yeah.
It brightened up. It's still being observed. It brightened up in the optical and in other wavelengths. It emitted a burst of gamma rays that was detected by gamma ray satellites. It emitted X-rays later on and radio waves later on. Still being observed in radio waves, although in the other bands it's now gone quiet. But it's taught us a lot about one of the fundamental questions in the universe, which is where the elements came from, the pollution that I talked about.
Yeah.
It turns out this is one of the major sources of creating elements, and but it creates the heavy elements, and the reason is actually not hard to understand, because this is a neutron star. As I said, it was held up by just having neutrons packed together. It's almost entirely just neutrons, which again don't like to be packed together, and so they resist that, and that's the force that's acting against gravity, the quantum mechanical force. But when it explodes, what happens is you get fragments of the star being pushed out, and they're all hugely neutron rich. You think of them as bunches of neutrons. Well, we know from our periodic table that you can only put nucleons together in up to a certain point before they just keep fissioning. They don't like to. So what these are just happening. These are just fizzling all the time. These things with neutrons are turning into smaller packets of neutrons, and they're producing protons and neutron mixtures and so on. And they're looking like mega heavy element nuclei. But they're just decaying all the time until they reach the stability region of the periodic table. But they reach it from above. They come in with higher masses, and they keep breaking down, and they sort of fill up, basically, the upper half of the periodic table, including elements that are essential to life, like iodine. Most of the iodine in the universe seems to have been formed by things like this. And so we know that we are products of stars. We know that all this elements that we're made of were created in stars. But what we didn't realize, or didn't accept, maybe, this proved it to us, because all these elements are being seen in this expanding cloud. What's being proved to us is that the half of the periodic table of which we're made was made in some explosion like that, maybe only one explosion like that, that happened nearby in our galaxy very long before our sun was formed, and then polluted that cloud that formed our sun. And that's where we come from.
So that's one really fundamental aspect of our understanding of the nature of neutron stars and how they affect their environment that this discovery has opened up.
Yeah.
I guess other aspects of that event were equally profound. One that I know is especially close to your own heart, having pioneered the method theoretically many years ago, and indeed that's just been recognised by the Royal Astronomical Society. They've awarded you the Eddington Medal in honour of that contribution. Perhaps you could tell us a bit about that. This is using gravitational waves to measure the expansion rate of the universe.
Yeah. 1986, more than 30 years ago, I realized, playing with the equations that describe how these stars come together, that if we could detect the signals from such events as we now have, we could interpret what we're detecting, we could interpret the signal and extract the information about how far away the signal was, how far away that system was when it was merging together and then exploding. And that's something that in astronomy is very, very rare, to be able to measure a distance. And that's because if you see a star, you don't know whether you're looking at a bright star that's quite far away or a rather dim star that's nearby. You have to have some idea what the intrinsic brightness is, the intrinsic luminosity. It turns out that because the stars, the two objects, whether they're black holes or neutron stars in these binaries, they're coming together because they're emitting the gravitational waves. The energy that they're radiating gravitational waves is the thing that brings them closer and closer together. It turns out if you can measure how fast they're coming together, you can actually get enough information to understand how much radiation, how much energy they were radiating. And that coming together is reflected in the orbital angular velocity. So the period keeps getting shorter and shorter. The orbit's faster and faster. So we measure these gravitational waves and we see a certain frequency, but the frequency is increasing, and we call that a chirp. It goes from lower frequencies to higher frequencies. Well, the rate at which it's chirping is the thing that tells us how much energy it's losing in absolute terms. So we actually can measure.
That's like knowing the luminosity.
That's like knowing the luminosity of the stars. That's right. So we know how bright it is there. We know how bright it seems when because we're measuring its waves here, and so we can infer the distance. And now, if you can do that, the prize that hit me right away as soon as I saw that, I said, "Wow! If we can do that, we should be able to measure the Hubble Constant." Because in 1986, the Hubble Constant is, well, let me explain. The Hubble Constant is the expansion rate of the universe. And it's a very simple, but probably the most fundamental number in cosmology. So if you have something that's expanding homogeneously, and by that I mean we can see the universe doesn't have any special location. Everything is moving apart in much the same way everywhere. And that means if something is twice as far away from you, it's going to be moving away twice as fast in order to preserve that sort of general level of no special place. And so that proportionality, how fast as a function of what the distance is, that proportionality is called the Hubble Constant. And it's measured in strange units called kilometers per second per megaparsec, because kilometers per second is how fast it's going, and then per megaparsec is the astronomer's unit of distance. So you want to measure that. And in 1986, there were two groups that differed by a factor of two. They had totally different ways of measuring. They couldn't agree, and this is the most fundamental number. And I thought, well, let's see if we can make a contribution to this. And it was clear that if we identified the neutron star pair that was merging together with an explosion, if we could identify it, then we could measure its recession velocity, or at least the velocity of the galaxy that contains it. And then we'd already have the distance from the gravitational waves. That's the key thing.
And they should be proportional to each other.
The velocity is easy to measure in astronomy because you have redshifts, the blinds, spectrum, and so on. So you can get it. And there are other ways of doing it, but that is the simplest way, and that's what presented itself in 2017. So we made the measurement. Now, we didn't have as much information as we would have liked about polarization and so on. So we had some fairly large error bars on our measurement. It was our very first attempt.
Yeah.
But the remarkable thing is the central value of our measurement came in exactly where the astronomers are right now with their measurements. Now, the astronomers have improved their measurement methods
a great deal since
a great
1986, but yeah.
But it happens that there are still two groups, two camps. They're very much closer together, not a factor of two. They differ by only a small amount, but they differ by a significantly small amount. And we came in right in the middle. So we're in the game. And when our detectors come back up, we're hoping we can sharpen up our accuracy with more events and make a difference to this discussion about what is the real value of this constant, which is now called, by the way, the Hubble-Lemaitre constant.
Yes.
We've, as astronomers, we've agreed that we should be honoring the name Lemaitre, who was the theorist, who took Einstein's equations and predicted that cosmology should be expanding and said to astronomers, go out there and measure it. So his name is attached to it.
If I may say so, that's mirroring what happened with the gravitational wave measurement of that constant, where you had the theoretical prediction in 1986, and then, 31 years later, we can do it for real. That must have felt very satisfying.
It was very, very satisfying.
Yeah.
And let me tell you another satisfying thing is that you mentioned that I've received the Eddington Medal from the Royal Astronomical Society. The very first person to receive that medal was Lemaitre.
Ah, I see. I wasn't aware of that. Excellent. We've followed very illustrious footsteps and very richly deserved. So we're almost out of time. Maybe just developing that just a little bit further. You mentioned in describing the detection of the neutron star that we were able within just a few hours to tell our astronomer colleagues that this, well, indeed, we told them much faster than that, but within a few hours they had identified the host galaxy of the neutron star merger. So I guess crucial for that was having a good ability to localize the position of the gravitational wave source on the sky. So looking ahead to what the future will hold, you've mentioned that we're about to begin taking data again quite soon, but a little further down the line, the reason we're here is because of the prospects for doing even better once we have a LIGO-India detector. So perhaps we could end by just reflecting on some of the exciting possibilities that lie ahead with LIGO-India.
As you're referring to, gravitational wave detection needs more than one instrument. The Americans built two, but really to get all the information that you need from a gravitational wave signal to infer the distance and all the other things you'd like to know, you need a minimum of 3 detectors. We were very fortunate that the neutron star event was observed just after a third detector, the Virgo detector, which is in Italy, just after it began observing. It was only a couple of weeks into its observing period, and it was able to make some crucial contribution that allowed us to localize. So our detectors are like microphones. They detect from all different directions. And so the only way you can localize is basically the signal arrives at this detector before it arrives at this detector before it arrives at that detector. And that will allow you to triangulate and get a direction in the sky. And so that's something that we only were able to do successfully with the 3 detectors. Now, the bigger baseline, the bigger separation you have between detectors, the more accurate that becomes. And it also depends a lot on how sensitive the detector is and whether the detectors have the same, let's say, frequency band of observing, or there's some parts that are not. So the nice thing that we're celebrating here is a third detector being built with exactly the same characteristics of LIGO, and built with a specification that we expect LIGO to be to reach also around the middle of the 20s, which we call A+, technical word for a much more advanced, a much more sensitive detector than the ones that are being operated right now. And with these very much improved detectors and good baselines, 3 identical detectors. The Virgo detector will still be in the game, and there's a detector in Japan as well that will start up next year. And so we'll have 5, but particularly with the 3 LIGO ones, we have a kind of reliable way of triangulating and
Yeah.
getting good positions on the sky for the next time and the next time after that, and we have a bigger volume that we can sense, and so we're expecting that these events are not happening just once every few months, but several times a month or more, and that we'll be getting black holes, thousands of them. So it'll be a very exciting time and for the people in India who are building this and who are interested in science and watching this happen. It'll be an exciting time.
Well, we've talked a bit about black holes, about their properties that, as we said, we would hope to understand better once we have a larger population of them to study. So the prospect of having hundreds, even thousands of such sources is of course very exciting. Maybe even more exciting though is the possibility that we'll discover something wholly unexpected.
Yes.
I guess if we learn anything from the history of astronomy, that usually happens when we open a new window in the universe.
That's right.
So if the next decade can be as exciting as the preceding one, then we have a great deal to look forward to. So it's been a great pleasure talking to you today, Bernard. Thank you very much.
Pleasure for me.